So we continue our discussion in chapter 18. This example is going to be about the multi-phase system heterogeneous chemical reactions. Let's consider like the reactor. Here we have some solid catalyzed inside of our reactor. So the gas is coming from this side, is going through the voids, through the end, and when the gas is just goes touch the surface of the catalyst, give the reaction of the two A's, give the species B, and we consider the stagnant actually when we consider the, for example, like a catalyst, spherical catalyst, around it a stagnant gas film, we call this gas film is happening. So the species in here in this gas film, the diffusion of the ice goes in this way through the catalyst surface, and species B goes in this way in the other side. So let's define our system. In reality, our system like this. We have some catalyzed spherical pellets inside of our reactor, but let's consider we have like reactors here. A is coming from this side, and let's say all this catalyzed inside of our reactor is in the uniform distribution. Let's say here like this, all this catalyzed is just has some uniform distribution like this, and so on. So the gas is going and past this just voids from between these catalyzed pellets, and let's consider all these catalyzed plates like just one system, one surface like this. This is the solid phase, and around here we have just some, the as A is coming from here. We consider the stagnant gas film. So that A is just diffusion is happening through the surface, and B is coming from this way, and B is going this way. So this just simplified system like here. The surface of the catalyzed system, just this is the film, and we call this the Z equal to 0 here. The A is coming from this way, and we call the Z is equal to this this thickness. Z is equal to that one as the film thickness. The Our system is like this. The A is coming from this way, and just diffusion is happening at the surface of the catalyst. The reaction is happening. 2A is cause B at the surface is instant. That means so rapid. So we don't see any A at the surface of the catalyst. Is A is instantly goes to B. So because A is coming from this way and B is going, then when the reaction happens, when the two A's they give the species B, and species B diffusion is happening through the reverse direction of the A. So based on the reaction, we can define that the total molar flux of the species B is equal to minus 1 over 2 is NaZ, and since the 2 moles A gives 1 mole B, so um, this is going to be species molar total flux of the species B is going to be minus 1 over 2 total molar flux of the species A. So then, okay, just from the definition of the total molar flux for Na in the z direction, we call this the z direction. We can write minus C dAB actual dxa dz plus xa Na and nb. This is our general relation. From here we know the relation NB is going to be equal minus 1 over 2 NAZ and BZ. From here we insert here, this is going to be plus this side XA NAZ minus 1 over 2 NAZ. From here we just obtain from here 1 over 2 NAZ. If we take this other side and we just manipulate, then we can obtain this time this molar flux relation. So molar flux is going to be in the z direction, in the dead z direction. We call this the positive z direction. Other side we call this negative z direction, positive z direction. We just obtain that relation. Now we can write here just the shell, very, we can just pick some delta z, very small z, and we can write just the shell balance. And if we write shell balance as NaZ minus S NaZ delta z is going to be equal to 0. If we divided this S over delta z and we take the limit delta z goes to 0, then we can obtain this differential equation for this system. Then we can take this and insert here like the previous examples for the solution of the system. Just take this insert here, we obtain that one. And actually if we integrate this 2 times, we obtain this form and this form here, and we can write 2 boundary conditions. We have 2 boundary conditions. When z is equal to 0, then xa is going to be equal to xa0. When the z is equal to that one is like a thickness of the film at the surface of the catalyze. As we said, this reaction happens very rapid, is instant reaction. Then we can say at the surface of the catalyst xa is going to be equal to 0. So for these 2 boundary condition, if we solve this equations, if we find these constants, we can find our concentration distribution by this form. By this form, actually, if we take this, let's in here for the total molar flux, if we take this concentration gradient and differentiate, then we can find that final form of molar flux for this system. Okay, in for the next example, just think about this time diffusion with a slow heterogeneous reaction. The problem is gonna be same as the previous one, but this time when z is equal to thickness at the surface of the catalyze here at the surface of the catalyze. This time we don't consider it is the rapid instant reaction, so we cannot assume our boundary condition this time is xa is to 0. This time at the surface of the catalyze, we have some reaction term in here. NaZ is going to be equal to K1 double prime Ca. Ca is going to be the molar concentration of the species A. We can replace this K1 double prime C. This is the total concentration in the binary system AB, and Xa is the molar fraction of the species A. Then we can everything is going to be same as the previous example, but only difference is going to be boundary condition 2. In the previous one, boundary condition z is equal to thickness is going to be xa was 0, but this time from here we can obtain xa is going to be equal to naz divided by k1 double prime c. So just take this just from here. This is going to be same also for this example. This is exactly going to be same, but this time our first boundary condition was going to be that one, but second boundary condition is going to be that one. Actually, just take this 2 boundary condition and solve this equation and find the constants k1 and k2 for these boundary conditions. And if we solve this, then we obtain our actually a final concentration distribution by this form, and we can write the total molar flux actually by this relation. So what is the difference between this problem and the other problem? Again, only the boundary conditions too. This time at the surface of the catalyst. In the previous one, the XA was as a boundary conditions was 0 because we assume is instant very rapid reaction, so we assume we don't see any concentration of the species A. But this time we have some uh, slow slow reaction at the surface. We define our um, we define our reaction and definition relation between the total molar flux and the reaction term by these formulas. And if we exchange in the previous problems boundary condition to by this new boundary condition, then again we solve this relation, we obtain that concentration profile and that total molar flux. This is the only difference between two problems on the boundary condition too. So anyway, just we continue our discussion in the next example. In the next example, we see diffusion with a homogeneous chemical reaction. Let's consider like a system. In our system here, we have some liquid B, and above this liquid we have some gas A. So diffusion of the gas A happens in this direction. When the gas A is diffused through the liquid B, so the reaction is happening. A plus B is give the reaction and gives produced another species AB. So when write just shell balance inside of the liquid B, delta Z shell balance, we can just Na is coming from this way and Na is going out, So, but this time we have just homogeneous reaction term, So for the shell balance, we can write this term is give the in, and this term is the give out, and this term is give the reaction rate inside of our shell balance. So when we divided this each side by actually S over delta Z, and we taking the limit delta Z approach to 0, then we can obtain this differential equation this time. This is going to be left side dNA over dZ plus the reaction term is going to be 0 this time. This time we have another plus term is reaction term. Then we can write for this system our NaZ as minus C dAB dXA dZ plus XA Na plus NB NB. For this time, just the species A is diffusion happens, and the other side. Further, for this system, the total molar flux we define beginning of this chapter as minus C TA B dXA dZ plus XA Na plus NB. For this system, just the species A diffusion is happening through the species B, so this is going to be 0. Then we can write this right term is going to be same, but this is going to be XA and A. but for this problem we can just assume in the species A through the liquid B, inside of this liquid B species A concentration is Ca too low, then we assume the right side, the second term in the convective term, just is very small respect to that molecular transport diffusion term. Then we can assume, we can just neglect that one. We can just take this part from here for this problem. Then we can obtain this relation for the total molar flux from here. So we can write that one as this form. So then we can take this and take this, insert here. If we insert here, we can obtain from here second order differential equations like this. We know from the mathematics the solution of this second order differential equations. So if we define because this is the second order differential equation, we have to define two boundary conditions. The first boundary condition is going to be z when z is equal to 0 from here, like here. This is the liquid, this is the surface interface between the gas and the liquid, gas A, liquid B. At the surface, if we define the z is equal to 0, at the z is equal to 0, the concentration of the A is going to be Ca0. When the z is equal to the L, that's mean at the bottom of the liquid, our boundary condition is going to be NaZ is equal to be 0, because at the bottom here there is no any flux term here. Flux term is going to be 0, or either we can write dCA or dZ is going to be 0, because after that point there is no species A concentration change in respect to Z, because this is just the bottom of our system. So this is going to be our two boundary condition from here. Anyway, so when we continue, if we define like here, if we define this the variables, we say we can make this equation, second order differential equation dimensions form like this. Then this is going to be Ca over Ca 0. Then this is going to be Z over L. This makes these dimensions forms, and this going to be that one here, this, and we can obtain our solution as this for the second order, this type of second order differential equation. We have two constants C1 and C2. When we apply two boundary conditions, finally we can obtain our concentration profile. That means that one Ca over Ca0 is going to be that one actually, and we can write this open form. This is going to be our final concentrations distributions for this system. Actually, this is going to be equal that one. Our concentration is going to be changed by this form, by this shape. Okay, this is another example of this chapter. If you just go move our actual final example in this chapter, in this chapter our final example is going to be about the spherical pellet. Let's consider diffusion and chemical reaction inside of porous catalyze. You know the catalyze. As a physical representation of the catalyze, we have through the inside of the catalyze we have some pores, and we have some catalytic surface, active surface. When the species A is diffusion happens through these pores at the surface of this solid surfaces, the species A is just gives reaction and give the product of B. So we just define our catalyst pellets like this spherical form, and this has just the radius of the R, and give the reaction of the A, B, just a stream with concentration CA, CAR and CBR goes around around this spherical fillet, because when this, consider this like the reactor, when the along the reactor length, the species A goes B, so this streams then contains the A plus B binary system. When this goes, the species diffusions happen in through the pores and is give reaction, and A goes through the pores and B goes in the reverse direction, so on. This is going to be our system, So when just we can write to obtain the to model the system. Let's consider these are the pellets, are solid pellets. Just we can write around solid pellets. Just we can write just the shell balance, just like this. Uh, Na Na R in, Na R out for the, actually this is the wrong one, the wrong representation. We should write like this. These are, let's go say these are the spherical pellets. Inside of our spherical pellet, we can just define some shell here. So the gas Na is coming from in through the shell and is going from alt Na R plus delta R, and in here the reaction also is happening. So this is our shell balance. So our shell balance is going to be this form. Actually here you see the first term is going to be in term, and second term is going to be alt term, and the third one is going to be reaction term. So from here, if we divide all every part by 4 pi delta r, and if we take the limit delta r approach to 0 like this, then we can obtain this this form of the differential equation for the spherical pellets, actually. So what we need to know, we just need to just find the relation for the total molar flux here, and just insert in and solve our differential equations. Again, for this problem, let's say our reaction is A gives the reaction B, then what's going to be relation? NAR is going to be minus NAB, because through the radius of the pellet, A goes in this direction and at the surface of the solid and give the species B, and B is go in this direction. So this is going to be positive, let's say R direction. This is going to be negative R direction. That's why they have the positive molar flux of A is going to be equal minus molar flux of N Na sorry MBR here. So this is going to be B here. So if you write the total molar flux along the radius of the catalyze, minus C dAB dXA dR is XA NI plus NB, since this is, or this is going to be minus NBR, let's call R, and this term is here is going to be 0, and finally we just obtain the diffusion term for this total flux. So that's why we obtain that form. And now take this definition of, or relation of, this total molar flux for species A, just insert here. When we insert here, we just obtain this second order differential equation. Then if we define like RI RA, here is the heterogeneous reaction rate, like here we can define that one, K1 double prime A multiplied by CA here. and we can just insert here, and we have that second order differential equations. Then we can define boundary condition when the r is equal to r equals r mean. Think about again the pellets. When at the surface r is equal to at the surface, then concentration is going to be CAR here. When the r is equal to 0 at the center, so Ci is going to be finite in the second boundary condition. So then we can make this dimensions form like this. Then we can solve this, and we can obtain this final form of the species A concentration profile along the pellet's radius. This is going to be our actual our final relation. Then we can obtain at the surface when the r is equal to r, the total rate of mass flow. This is going to be kilogram per second or no mole per second. We can obtain that relation. This is going to be that one actually. Similar to other example. In here, this is going to be another term at the surface. At the surface, we can write the surface reaction term by this, and taking the ratio of the last two equations. What the two equations? This expression is the total mass flux in terms of the mole per second, and the surface reaction rate in terms of mole per second. If we divide this term, we obtain just the effectiveness factor here for this catalyze, and here this term is um, we just call that one here by this formula for this catalyze. So actually this is our final example in this chapter. In the next chapter, we will just go in chapter 18, and we will go and equation of change for multi-component system, derivation of the equation using the Raynaud transfer theorem, and then we will just go and review some examples and how by utilizing the appendix and the table of the species mass conservation laws, equation of change for the multi-component system, and just go review some basic examples. So see you in the next video.